Hi, welcome to Engineering 255 Statics. Today we're going to look at the chapter 10. In this video, we're going to look at moments of inertia, and particularly we will look at the moment of inertia's four areas. There are several different moments of inertia that we will cover in this chapter. We're going to skip some of the sections. You will see what are the material that we will cover. So let's look at what is the definition of the moment of inertia for areas and the radius of the gyration of an area. And today, by the end of this lecture, you should be able to define the moment of inertia for an area that we abbreviate as the MOI, that represents the moment of inertia. And you're also going to determine the moment of inertia by the integration. So there's some math that you have to do, and we'll show you. This is very similar to the previous chapter. You're looking at how do you find a centroid, and that is very similar to that. Let's begin with a common structural design questions. Why do beams and columns often use like I or H or C shape cross section instead of like a solid or circulars? Well, the reason is how the material is distributed in a cross section. That distribution will affect the moment of inertia. This is related to the beam's resistance to bending. Okay, we're not going to talk about how you use the bending moment, but this is going to be one of the major effects that will change the moment of the bending. That moment of the bending will represent how much of the load is going to apply to the structure. Um, Here's another real-world cases. Why are hollow tubes often preferred over the solid rods? Well, obviously the solid rod costs more, um, but it is also about like optimizing the mechanical performance of the shape. So the shape really plays an important part in the statics when we look at the moment of the inertia. So to evaluate and compare such shapes, we need to understand and compute certain parameters, and that include the moment of inertia that influence the stiffness and the strength of the material. Now let's look at the definition of the MOI for areas. Let's define this. So consider there's a plate, and this plate is submerged in the liquid. So here's the liquid, and the plate is underneath of the liquid. And for the liquid, it will apply pressure to the surface that is underneath that. And in the physics, you learn the pressure force is proportional to the depth. So depends on the distance of y, and we can find out the pressure, which is equal to rho times y. The rho is simply just like the specific weight of the liquid, and use that times the y represent how much of the pressure that is applied to something below that. And the pressure is also related to the force, right? So pressure is actually equal to the force divided by the area. So if we want to find out how much of the force applied to the plate, by knowing the pressure, then we multiply with the area, then we will be able to find out how much of the force is applied to that. And once you know the force, if you multiply with the distance, which is the y, then you got what we call the moment, right? So the moment about any of the axes, in this case, is about the x-axis. If the force is also is at this direction, then you're looking at how does it rotate around the x-axis. In that moment, it's going to be equal to y times the force. where the force is equal to P times dA. And the P is equal to rho times Y. So we put all these together and you do an integration by looking at the overall moment, which is the total moment, and that is the equation they ends up with. So rho times the integration, which is the area integration of the y squared dA, this is actually represent the total moment about an axis. The same kind of an integral expression appear in the solid mechanics when we analyze the stress and the diffraction in the beams. But we are not going to cover this part, but you have to know how to get this part first. Now this type of integral is what we call the moment of inertia of the area, because we are integrating with respect to the area. And if you remember the equation, there's an a squared involved. Let's consider different cross-section shapes with the same area and the material. So all these shape A, B, and C, they have the same area, right? For example, this one here, this is 10 by 10 high and width is 3. This is a width is 10 but height is 3. Very interesting. They have the same amount of the area. And you might think, well, it's going to support the same amount of the strength, but the answer is no. It depends on the load, and this actually will have a different of the strength, which means it has a different resistance to bending. It depends on how the orientation is. And that is the reason why we have to do the calculation. All right, so that's here we have a very practical example. The total moment of inertia, we want to calculate that. And if you have a vertical loading P and you apply it to the beam, right, which is the one that we just showed you, the three beams section are loaded identically, but their shape are different. Now, which one experienced the least diffraction and internal stress? That is the question that we wanted to find out. Okay, so for the differential area, the dA, showing the figure in the previous slide, they will have a different, because when you do the cross-section area, and you will find out it's going to be different. Now, in this, if section A, because it has the highest moment of inertia, most of the area is loaded further from the x-axis, so the distance square really matter a lot. Okay, which this really means that if you remember, let me just draw the shape of that. So the first one is like an I shape, right? And the other one is going to be like this, and the third one is like a horizontal. So most of the area for this I shape is actually away from the middle line here, which is the rotation of the axis. This is the more concentrated, this is more distributed. So more distributed is actually going to give you higher of the moment of inertia, because the distance of the material away from this middle will, well, I should say the distance of the area that is away from this one will give you a higher of the calculation, and it will give you a higher moment of inertia. So the total moment of inertia is calculated by integrating over the entire area. This entire area, the dA, you have to pick which slice you're going to cut it when you see an area. And this is why we also refer to the moment of inertia as the second moment of the area. because it has the square. Okay, it has a square of the distance. This is with respect to the x-axis. This is with respect to the y-axis. Okay, and that is what we call the moment of inertia. Now, if you look at another one, this one is the polar moment of inertia. When you do a polar moment of inertia, you're looking at the distance, the radial distance. If you define this as the radial distance, this r squared is actually equal to x squared plus y squared. So this j here is going to be equal to the ix plus iy. By definition, ix and iy is the y squared dA and x squared dA. So the polar moment in inertia is going to be equal to the sum of these two moment of inertia of the area. The unit is important. It has a unit, and if you look at the unit, this is a meter square, right? If it's a meter, the area is also a meter square, so it's going to be the length of the force order. So you could use inches as well, but it has to goes to the force power. Let's show you the example how we do this kind of a calculation. So we're going to start with slide. When you calculate that, use the integration, you have to start with a differential area of the element. So here we use this one as the area. This is just an arbitrary shape, right? You have an arbitrary shape, but you start to slice the shape with smaller area. Then you either choose vertical or horizontal. Again, you will prefer to choose the area that you can have a continuous way to identify the height. This decision affects how complex of the mass. So you want to choose the one that will give you a simple integration. And that really is the case by case. After you select the area and the element parallel to the axis about which the moment of inertia is to be determined, usually result in an easier solution. That's what we just emphasized. So when you select, in this example here, you select this vertical one, right? And you are going to determine which moment of inertia. This slide is going to determine the moment of inertia of the y. So this one actually is going to help you to find I sub y. If you do this horizontal one, and this one will give you the I of x. So when you do this one, you integrate from the bottom, goes all the way to the top. You are looking at how does it rotate about the x-axis. And think about the equation that you have if you're looking at I sub y, and you're going to have the integration of the area, and that is going to be y squared dA. And then you, the dA in this case here is going to be equal to y dx. And when you put y dx into here, you find out this is I cubed dx. And since we're integrating with respect to the x, you have to represent y in terms of x in order to finish the integration. So this is very similar to the previous chapter. So and that's what I showed you before. And in order to get the solution, you really have to know how to represent and how to select the slice such that you can finish the integration. Let's use a real example to show you how to do this calculation. Over here, this example, the task is to calculate moment of inertia about the x and y axis. Okay, so we begin with a slice. If we wanted to calculate I sub x, and which way that you're going to slice this element, and we know that the A is going to be equal to how you slice it. If you are trying to find out how does it rotate about the x-axis, you will go horizontal. You're not going to go vertical. So we're going to slice this one horizontally, and this much of the distance is equal to dy, and this one is your x. This is what we call the dA. So this is your dA. So in this case, dA is going to be x dy. We're going to put x dy in here. You're going to have a y squared times x and dy. Okay, now the question is, how do we represent x in terms of y? And you look at this equation right here. This is the equation of this line here. That means when x at a certain amount, the y value is equal to y cubed is equal to x squared. But what is this x? Because this is an area, right? So if you wanted to find out this one here, this length is actually equal to this 1 meter minus how much of the y that is, right? So you have to find out what is the value at here. That value is determined by this one here. So if you represent x, and that will be equal to a square root of y cubed. Or you can write this one as the y of 3/2. So x is equal to this, but the real length, I know we use x a lot, but actually what you try to find out is the length of this one here. This actually is equal to, let me put x prime, that will be, I will distinguish this one with this one here. So let's just say this is going to be x prime. The area is going to be x prime times dy. The x prime is equal to 1 minus this value, which is y 3/2. And that is why we put this one here. That is your dA. And then you multiply with the y squared, and then you do the integration. So when you multiply this all together, you have a y squared minus y. You're going to add 2 to this one here. So when you add 2 to this one here, that will be equal to 9/2. Okay, and then you do integration. You take the order, the power to be the number you divide, and that will be the integration from 0 to 1, and that is your Ix. Similarly, if you wanted to do Iy, and then you have to do the slice, which is a vertical, right? So let's do a vertical slice. When you do a vertical slice, and this distance is what we call the what? Dx. This height is determined by this equation again, and because it starts from 0, you simply just need to represent this y in terms of x. So the y is equal to x of 2/3. And our area is going to be, the dA is going to be equal to y dx, where the y is equal to this. And that's exactly what you see here. And since we're calculating the moment inertia of the area for y-axis, then this is going to be x squared, and this will be very simple, and you do integration, and that is the answer for that. So you can find out ix and you can find out iy, and this is the one that you calculated.